All right, so in this lesson, we're gonna work with limits, and our goal is essentially to just gain understanding of when limits exist and when they fail to exist. And when they do exist, we want to know how we can, estimate it using graphs or calculations and so forth. So it's kind of just again like a general overview of the concepts of how a limit looks, graphically as well as, numerically. So let's say we have this function, f of x is equal to x cubed minus 1 over x minus 1. Most likely you don't know what this looks like off the top of your head. I don't expect you to. So if you were just, to kind of get an idea of what this graph looks like, and we're assuming that you don't have a computer or some graphing calculator where you can just plug it in and see it. So the general technique is plug in values for x, and get a sketch of what the points will look like till we get enough of them to make an act to be confident that it's gonna be what the actual function looks like. Now you can notice in this graph that if you plugged in 1 for x, you would get 0 over 0. So it wouldn't really work, or we would say we would have what's called an indeterminate form, and you may have learned for x equals 1. But we can gain an idea of what happens with the graph near 1 if we plug values very, very close to 1. If we plug 1.01, 1.001, and as well as like numbers below it, 0.999, 0.99. That's going to give us an idea of what the graph is doing when x is actually 1. So we're going to basically, practice this, I guess you can call it plug and chug approach. So we plug 0.75 first into x, 0.75 cubed minus 1 divided by 0.75 minus 1, and you would get about 0.3125. Now I'm just going to go ahead and write what the values are because I've already done this, and then just to save time with the video. But I definitely advise you to do really when you first get exposed to this, it's important for you kind of just to get that practice, but also just to gain that intuitive and understanding of like how these values behave when you're trying to find a limit, because it's not always that obvious. So really take the time to plug the numbers in. Anyways, you would get approximately 2.71 for that, and then the 2.97 and 2.997, and then when you plug in 1.001, you get about 3.003 and 3.030 rounded, 3.310, and 3.813. Okay, so we don't know, our questions, what's going on at 1, but if you look at the values, it's probably, maybe it's 3. We can say maybe, is it 3? Put a question mark, the value 3? Well, I actually know what this graph looks like, and you actually be surprised that it's actually just a parabola. That parabola is going to, look something like this. It's a little crooked, but it's going to, have a y-intercept 0, 1, and 1, negative 1, 1. Let me draw this little. Now, so what's going on when x is, when x is 1? Well, what's actually going on is that you have a discontinuity. or we can call it, we also call it a hole. So the graph, we say, the graph is essentially a parabola with a discontinuity, you can say gap or a hole at 1, 3. Now, to help you get a better understanding of, of what's going on here, I've actually, taken the liberty of, graphing this with a graphing calculator. So here it is. Now, let's see what's, let me zoom in here. Let's see what the graphing calculator does, because, we're always like, oh, well, why do we need to do math by hand when we can do our calculator? So let's trace this, and let's see what's going on when x is 1. And you can actually see that that it tells you that it's undefined there. As soon as we go to the right, it's 1 point. It has a point there. Now, the thing you have to be careful about is that the graph, doesn't just explicitly show there's a hole there. So if you just graph this mindlessly without thinking, you wouldn't think there's a discontinuity or a hole there. So be careful about that. Because the calculator, it won't show that. Anyways, so let's get back to let's look at another one. Oh, before that, so what we can say when we're talking about limits, so we have the limit of this function as x approaches 1. We say a limit as x approaches 1 here is equal to 3. So the formula, we have this notation. We abbreviate limit with, just LIM. And so we're basically saying as we get very, very close to point C, it's going to equal some value. If it does, we would say that the limit of f of x as x approaches C is equal to L. So in this case, we could say, let's actually write it out. The limit as x approaches 3, x approaches 1. Let me erase that whole thing. And let me use pencil. The limit as x approaches 1 of this function, f of x, is equal to 3. Practice writing this notation. Don't just get lazy and just assume you understand it, because I've learned that one of the biggest points of confusion that gets students off to a bad start in calculus is that they kind of get lazy when they're writing this, and then they write it wrong, and then when they're seeing it in textbooks and doing their homework or on tests, they start getting confused, because we're going to learn about one-sided limits, positive, negative, approaches. We're going to look at combining, limits of different functions. So notation is key. So really practice writing like this. Like this part right here is a subscript, or it's right below the limit. This is right here is going to be where your equation or expression is. And so really practice being detailed with it, especially at the beginning. Okay, so now let's look at another one. So let's say we have this function now. F of x is equal to x all over the square root of x plus 1 minus 1. Now, again, if we plugged in 0 into here, we would get 0 over, square root of 1 plus, so we get 0 over 0. So we get an undefined value for that. So but we want to see, what's going on as we approach 0. So we would, pick values that are very close to it, to plug these values into this expression. So values below 0, values above 0, so the positive side, negative side. So we can represent this as like these values are approaching 0 from the left, and these values are approaching 0 from the right, or positive side. We're approaching that number. Let's write that out actually. Approaches 0 from left, versus 0 from right. Now, since I already calculated this, and just to save time with the video, I'm just going to write in the values. But again, really make sure you practice with these calculations. I know it's a little tedious, but it's really going to help you down the road because you're gaining your basis of the understanding for limits. Anyways, for this we would get 1.999499, and then we would get up 1.99950. I'm rounding these to the fifth significant, 1.9995. I'll lose my concentration. Then on the right side, we get 2.000005 and 2.00050, and then 2.00499. You can probably guess that, maybe it's approaching 2. You say it's approaching 2. These values are bigger than 2, and these values are less than 2. So now let me give away the graph. This graph would look something like this. Your XY axes. We're going to have a tail here, -1, 1. And at 0, the value is 2. And again, we have a hole. We have a hole at 0, 2, or point discontinuity. So again, we can also say it's undefined at x equals 0, and its graph has a hole or gap or discontinuity. So same idea as the previous one we did. If we were to actually graph this using technology, you wouldn't see it again easily. We would trace it, and you would see that then it would be undefined there. So now let's look at a different situation. Let's say we got the piecewise function where f of x is equal to 1 when x is not 2, and then f of x is 0 when x is equal to 2. Now, don't overthink this one because this graph is actually fairly simple. It's just a horizontal line, remember? The graph is just a constant. So if we were to draw this, their function would be like something like this. Horizontal line. Goes through the point, 0, 1. But at x is 2, we have a hole again. At 2, 1, we have a point discontinuity or a hole, but instead you have a point at 2, 0 because we're told that the function is equal to 0 when x equals 2. So again, we have a point discontinuity, but what would the limit be? What would the limit of this function be at x equals 2? So the question is, if I want, what is the limit as x approaches 2 of f of x? What would that be equal to? Now, let's think about this. Remember, the limit is the value that you're approaching, not the value necessarily that the function is equal to at that point. It's the value that the function is approaching for, in this case, 2. And the value and the function is approaching this hole here. It's approaching 1. Even though it's not equal to 1, the limit is still going to be equal to 1. Or even though the function's value is not equal to 1 when x is 2, the limit is still going to be equal to 1 because it's approaching that point. So we say the limit of f of x as x approaches 2 is equal to 1. Now let's look at some cases where the other cases where the limit fails to exist. So let's say we have this graph. Let's see if you remember what this would look like. You can always, again, plug and chug, get an idea of what is going on with it. But this is actually an important one that you need to recognize and become familiar with, because these ones pop up on your AP exam, pretty much all the time. You don't get many, but you'll at least get one or two. Like some of these multiple choice, some of these will be part of the Fourier response. So make sure you become familiar with it. And again, just plug in numbers. Now let's see what's going on. We know it's not going to be defined at 0 because we'll have 0 over 0. But on the right side, since the value will always just be 1. So what's going on is that we have let me actually use a color pencil. We have a hole at 0, 1, but the graph is a horizontal line going like this. Say y equals 1. On the left side, you have a hole on this side at 0, negative 1, because the graph is a horizontal line that's equal to the line y equals negative 1. So then, again, let's say that let's have f of x be equal to the absolute value of x over x. So we can say this is our graph. This is our graph f of x. And so what's the limit then? What's the limit of f of x as x approaches 0? So let's write that, the limit as x approaches 0 of f of x. What would that be equal to? Now let's think about this. When x is approaching 0 on this line, it's gonna approach. It's gonna be equal to 1. The y value is 1 on this line. But when you're approaching 0 on this line, the y value is negative 1. So it's like, so what's the answer then? Now this is a case, the limit does not exist. It does not exist because the graph approaches a different number from the left side than it does from the right side. We can say DNE is common abbreviation. So let me write a little breakdown. The graph approaches different numbers from the right side and then the left side. From I hate squeezing my writing from the right side and left side. Should have wrote a little bit higher, but okay. So that's one example of a limit that does not. Okay, so now let's look at another one. Okay, so let's see what's going on with this graph on the limit of 1 over x squared as x approaches 0. So let's make again. Well, let me write it actually. Let's let f of x equal 1 over x squared. And if you recall from pre-calculus, this is going to be like a I wouldn't like think of it as like a dart or like a. But it's gonna look. Where should I put this? Let me put it over here. I want to have enough space to draw this. But the x values will always be positive. Remember, the x values will always be positive. On the left side, it's gonna be curving upwards like that. I like to put at least a point, -1, it goes through -1, 1. And on the right side, it's going to be curving like that. So it has an asymptote. It has an asymptote for x equals 1, if you remember that. So then the question is, what's the limit? What's the limit of f of x as x approaches 0 for f of, what's the limit of f of x as x approaches 0? Let's write that, the limit as x approaches 0 of f of x. What's going on? Now, here's the thing. We established that it's in this case it's approaching it's going it's getting very large from the left, and it's also getting very large from the from the right. So we know that this number it's basically what we call it infinity. Now you're like, well, it's approaching infinity from both sides, so we could say a limit exists. Well, sort of. We don't really think of infinity as a number in the mathematics world. It's more of a behavior. We think of it as a behavior. So we say that the limit does not exist as well. Now, it's actually not wrong to say that the limit equals infinity, because that's also another way to answer this question correctly. So don't think you're you're not wrong if you're thinking the limit is infinity, but infinity is also something we think of it not as a number. So since it's not approaching a number, we say the limit does not exist. But yeah, it is approaching infinity. You're right. Now that being said, so it's not always that when a limit doesn't exist that it's approaching infinity, right? So again, be careful. Make sure you use the right wording, but it technically wouldn't be wrong. And I did check this before. On the AP exam, they wouldn't mark it wrong if you wrote that this is equal infinity. So just be careful though when you use this. Now what we say is that f of x increases without bound. It increases without bound, and again doesn't approach any actual number, but it does approach again it gets infinitely large. So we could say as x approaches sometimes we say blow up. I like to say the graph blows up. But again, the limit does not exist because we're not actually approaching a number, because we don't consider infinity a number. I don't want to sound like a broken record. But anyways, now last one. That's what happens with this graph. Let's why we have the limit as x approaches 0 for the sine of 1 over x. Now this is a cool one. So this one is actually you can't actually expect to do this without technology, but they won't expect you to know this without having technology handy. So let me actually bust out my graphing calculator and let's see what's going on. Now, if we look at this graph, you can see it does something strange. So let's zoom in the center first to see what's going on when x is 0. Zoom in again, zoom in some more, and you can see this graph does this crazy thing where it just balances up and down. It oscillates, we call it. It's oscillating, like crazy. It doesn't stop. We zoom in more. You can see my scale is 0.02. Going more, 0.01. It just becomes a bunch of crazy lines. So it's like, what's going on? Even ridiculous. Now, what happens if we trace it? We go to 0, it's undefined. The calculator doesn't even know what to do. We move a little bit to the right, it does something, it's using, since we're at very small numbers, it's bouncing. See, look, we go 0.01, and then we go all the way down to -1. Now let me bounce to the left. 0.009, I barely shrunk, and look at where I'm at. The values are just, changing, without any, predictable, in any predictable manner. Not even this calculator can do it. And this thing costs almost almost $200 actually. Anyways, so let's just draw a sketch of what's going on. So the graph is actually bounded by the lines y equals 1 and -1. It's not a very good drawing, but okay. And it does something like, it does some okay. It's okay until it starts getting very, very close to 0. And I need a different pen. I'm gonna try to use. It just does this crazy, sort of oscillation thing. Eventually it veers off like that. But you get the idea. It's not a very good drawing, but it's all right. So we say the graph oscillates. Again, we'll define f of x as sine of 1 over x so as x approaches 0, fix that. F of x oscillates between -1 and 1. Oscillates, I believe that's how you spell it. I like the word, it's a cool word. It helps, I kind of actually think it helps me sound smart. Between -1 and 1. So again, we say, so if the limit as x approaches 0 of f of x does not exist. And D and E is usually an okay way to mark it. Okay, so what we learned is 3 common types of ways that a limit fails to exist would be it approaches a different number from the right side of C than it does from the left side, or it increases or decreases without bound. It goes to infinity or either negative infinity. We saw the one that went to infinity, or it can oscillate. It oscillates in this case between -1 and 1 infinitely. It doesn't approach anything. So it's just 3 general ways, and those are pretty much all the ways you typically need to know for calculus. But we'll see some good examples as we move through this unit. Okay, now let's look at this last set of graphs to understand how a graph may look different but have the same limit at a point. So here we have, I make this dark because this graph you can't actually see it. So we have this point A, this L. So we have a filled-in circle for this. And for this graph, we have an open circle at A, or at that point we have we have a circle there. That's again point A, L. And here we have an open circle, and only an open circle, no closed circle here. Okay, so what's going on here? So for this first graph, this is our function. We'll call it, that's our f, it's our function f. As we're approaching, A from the left side and from the right side, it's going to basically just be equal to whatever the y value is at that point. So we say the limit as x approaches A of f of x is equal to L. L is, represents that y value, whatever that y value is. This is probably the most basic case that you know. So, this is continuous. Continuous at, at A. Now, in the second case. The second case, we have a hole, but let's call this F. But we have this point here at A, and F of F of A. But even as we approach A from the left side and right side, you're still approaching this circle, or this this hole. There's a hole here. And again, it doesn't matter that the function is not equal to the value of y at that point, as long as the graph approaches that point from both sides. So we can still say that the limit as x approaches A of f of x is still going to be equal to L. So we could say even though, let me fix that up. Even though f of x or f of A is not equal to L. And our third case, here we have just a hole here. We have a hole. There's still our graph F. And so as we're approaching the point A from the left and from the right, it's still going to have that same limit. It doesn't matter that that the function doesn't have a value at A. It's still approaching the same point from the left and right. So we can still say that the limit as x approaches A of f of x is still equal to L. And we could say even though f of A does not exist. And it's not, again, remember, it's not necessary for it to exist in order for there to be a limit there. All right, so there you go.